And when we update at each stage, we utilize the neighbor's label, right? So to compute the probability of the labels of node V is equal to C. In short, YV is the same as C. So we get to compute the probability. We summate and normalize the neighborhood's probability. So quite similar to the graph convolution neural network, right? So actually that is inspired from these settings. So we try to, by looking at the neighbor's probability with respect to class label C, we get the average and update at each step from the initialization. But we difficult to expect convergence is guaranteed, right? Because we just keep averaging and keep propagating the labels. So for that reason, convergence is not guaranteed, and model cannot use feature information. So we initialize as 0.5 if we don't know about the labels. If we understand the label, if it belongs to class 1, you put the 1, and otherwise we put the 0 for the class 0, in this case red nodes. That's why we have just 0.5 and 1 and zeros. They're all labeled nodes with the label. So this is the initialization. And the first iteration for the node 3, and the sequence of the updates could be randomly determined. In this case, we follow the order of the node ID. So 1, 2 have their own labels from the training data, and node 3, we don't know the labels, so we just average from the neighbors. We see the neighbor, what are their neighbors? So 1, 2, and 4, right? 0, 0, and 0.5. And their average is equal to 0.17. It is a simple arithmetic average. And node 4, it is connected to 5, 6, 3, 1, 2, and we can utilize the updated probability if it is available. We just look, so probability is currently updated, right? And we just average from 1 and 3, 1 from the 0, and 0.17 is from node 3, 0.5 is from node 5, and 1 is from node 6. So we have 4 neighbors, and then average. And we can put the new probability for the node 4. The next is node 5. Similarly, we average the probability by looking at the neighbor's probability. And with this way, we can update over the unlabeled nodes. The second iteration, when we finish it, we see that we keep observing that, so compared to the first iteration, the probability of the node 9 is the same as before. So we can determine that it is converged. And third iteration, the probability of node 8 is the same. And we can also think as, oh, it is converged. And then keep having more converged probabilities at the fourth iteration, and then we see all the probabilities are converged. So by looking at the probability, we currently assume that threshold is from 0.5, right? So when the probability is larger than 0.5, we assign class label 1, otherwise we assign class label 0. But in the previous one, do not use node attributes, right? So how can we leverage the features? The main idea is that a classified node V based on each attribute FV as well as the labels ZV of the neighbor set NV. In short, we use the neighbor's label and their own attributes at the same time. So we utilize both of the information. This is a setting, so we introduce two classifier. So first one is, so classifiers are given in the below, right? Pi1 and Pi2. The Pi1, we predict node labels based on node feature. Another classifier is to predict a label based on the node feature and the labels of the node V's neighbors. So to get the ZV, so in this case, we keep saying that neighbor set, neighbor node label. So we introduce summary ZV. So for getting summary ZV from neighbors, we can utilize multiple ideas. For example, we can utilize histogram of the number of each labels, because by looking at the neighbors, we don't expect they all have the same neighbors. When they have different class labels, we can get the histogram from the observed class labels. And the histogram information could be a vector for the node V. Or we just use most common label as a feature vector. And I'm sorry, the summary vector, ZV. And third idea could be from the number of different labels. It means it is deeply related to confidence, but not directly, not the statistic confidence, but sometimes it helps to summarize the neighborhood. This in respect to the diversity, how much it is exposed to the different communities and could be related. So depends on your data set. So these are three possible ideas. So in summary, so in phase 1, we classify based on the node attributes using two classifiers, so which are explained just before. For train classifier, we have multiple options. The linear classifier, SVM, the even neural networks. At phase 2, we iterate till the convergence. On the test set, set labels based on the first classifier and compute the summary ZV and predict labels with Pi2. Repeat the step. We update the ZV based on the previous prediction. We update Y. We iterate the steps. Let me give you an example once again. In this idea as well, the convergence is not guaranteed. So this is an example. We may expect a graph of web pages, and node means web page, edge means hyperlink between web pages, drag edge means a page point to another page. Node features mean the web page description. For simplicity, we only consider two binary features. The task is that predict the topic of the web page. So we have simple baseline the baseline could be from the trained classifier, which classifies pages based on the node attribute. So in this setting, we assume that node attributes are available. We just predict the labels. But when we see the long prediction from the baseline, because it isn't it does not use the relational information. So each node maintains the summary vector ZV of the neighborhood labels. And so we also introduce two different information vectors, and I means that the incoming neighbor label information vector, and O is outgoing neighbor label information vector. So I0 equals to 1 means that at least one of the incoming pages is labeled as 0. Then below we have the information. So FV, they are feature vectors. So it is predetermined. So we don't modify. And I, this is incoming neighbor labels. So from the incoming neighbor, for the I'm looking for my cursor. No, I may not realize. So okay, so upper left node, the green one. So you see FV has 0, 0 vector, and I has 0, 1. O has 1, 0. So this is their incoming outgoing vector, because it has an incoming neighbor from the left bottom one. So it has a green one. So when you see its label, currently it is labeled as the green, and we put 0, 1. For the outgoing, currently has the red label, not the color, and the color of the text from the local baseline, right? The previous one. So we have different incoming and outgoing vector. And similarly, the left bottom one has different incoming and outgoing vector. And center one has two outgoing vectors, which have green and red. Right? So that's why it has 1, 1. And just follow the figures. And now we have three different vectors. FV is feature vector, I is incoming neighbor label vector, and O is outgoing neighbor vector. And at the first step, a different training set, so we train two classifiers. So node attribute vector only for the green circle, node attribute and link vectors for the red circle. And we train the classifier. So remember that the pi 1 and pi 2, right? Pi 1 takes just attribute vector, pi 2 takes all the information. And the step 2, we need to apply the trained classifier to test set. On the test set, we use trained node feature vector to set the labels of node, the V of the training set. So to Uh, so this is example. So if we don't utilize the neighborhood summary, the neighbor summary, so we get the wrong prediction, right? So we just giving the example, and we also we need to apply in any case the test set from the first classifier, and now we have the second classifier, and we can modify the labels. So before we move on to the use case of, the how to use the function 2, pi2, at this step 3.1, we update the summary vector zv for all nodes from the assigned nodes. So in this case, from the trained classifier pi1, we assign their temporal labels for the test node, right? And now we construct I and O at this stage. From the pi1, we construct I and O, and then we classify all the nodes with the pi2. So now we have pi2, so we utilize 3 vectors at the same time. We can assign the new label, and then we are able to see that the wrong prediction is corrected. And then we keep update the relation of features and labels until the convergence. So at this iteration, we often see that the incoming and outgoing vectors are changed. We stop iteration when we observe convergence or when maximum iterations are reached, because their convergence is not guaranteed, and we introduce another type of parameter, maximum iteration. When the iteration reaches to the maximum value, we stop updating. So that was the collective inference, and with or without the attributes. And third one is the loopy belief propagation. So it is a more probabilistic setting. So we introduce a message in this case. So literally, so we can understand the loopy belief propagation as we propagate belief. Basically, we assume that there is prior belief per node, and relates back to the class label. So the belief is propagated using the messaging function. So we send the message from sender to the target, from the source to the target. Apparently, the message depends on what the source node hears from their neighbor, and each neighbor passes the message to another node, which is connected to the node, the corresponding node, their belief of the state of the node V. So we still need to initialize the belief, right? It's similar to the previous, the 2 algorithms, but this is a more probabilistic setting, not just utilizing trained classifier, and we can define the function as the message function in this case. So we try to generalize the message passing. In this case, we utilize mi to j. So the green arrow send message from I to j to compute the message. We sum over all the states, which means the possible labels, right? And it sums over first. We assume the priors. So the priors are initialized, and that means the red square, and blue square is to consider all the neighbors. In this case, we product all the messages, and then we can see that the label potentials. So we also get the label potentials in this case. For getting the label potential, so it is something like the transition probability between the labels. So we have, when you assume the two different labels, we can compute that how often the label is changed, right? So it is computed from the current observation, and by looking into these mathematical computation, we can compute the message variable. And from the computed message to get the actual belief after the convergence, so we repeat this process till the convergence or till the maximum number of iteration. We compute the belief using the all messages from the neighbors and the prior. So this is a belief. By using this, we can predict the labels. So this is called the loop belief propagation. Today we have talked about the relational classification. So it iteratively updates probabilities of node belonging to a label based on its neighbors. And second one is iterative classification. It can improve over collective classification to handle attribute feature information and classify node I based on its features as well as labels of the neighbors. Loopy belief propagation is quite different from the first two, but still utilizing neighborhood information using the marginal distribution. We update the belief and we get the final prediction. So these were quite dominant before the graph neural networks and node embedding, and it worked their prediction actually on the graph space. So this is from different from the embedding level, so low dimensional, the representation level inference and classification. But we don't use their idea, the actual implementation, the exact same implementation. We don't use these days, but mathematically or intuition wise, we use still use their idea in the graph neural networks and node embedding. So when you read articles and you still likely to observe the terminologies and the intuitions. So still it is important to understand these three, the ideas and the intuitions. And I'm supposed to give this lecture before the graph neural networks, but you have to prepare. You need to have the more time to the experience the network embedding and graph neural networks, and so I slightly changed the order of the lecture. Well, timeline wise, it should be before the network embedding and graph neural networks. That's all. So if you have any questions, let me know. And thank you for your attention. And see you soon. Bye bye.